Scientists have observed a puzzling event related to the Higgs boson, which indicates that our current understanding of the particle may not be correct. They have witnessed an unexpected decay of the exotic particle that surpasses the boundaries set by the standard model of physics. These surprising findings challenge the predictions of the standard model and suggest the presence of new physics. To comprehend what has been observed, let me briefly explain the concept of the Higgs boson and the Higgs mechanism using a daily life analogy. We can picture the universe as a vast swimming pool, not filled with water but with an invisible substance called the Higgs field. Now, envision different types of swimmers within this pool. The first swimmer is a professional who swims efficiently, swiftly cutting through the water with minimal interaction. This is similar to particles like photons, which do not interact with the Higgs field and thus have no mass. Next, consider a casual swimmer who may not swim frequently. They can swim, but they create splashes and waves, finding it more challenging to move through the water. These swimmers represent particles such as electrons and quarks, which interact with the Higgs field and thus have mass. Now imagine an inflatable beach ball in the pool. It cannot move on its own and requires effort to push it around. We can think of this beach ball as heavier particles like the W and Z bosons, which interact with the Higgs field extensively, resulting in a significant amount of mass. Lastly, picture the waves that move through the pool as disturbances in the Higgs field caused by the interactions of particles with it. These waves are fundamental to the Higgs mechanism and provide other particles with mass. The observation of unexpected decay in the exotic particle suggests that our understanding of the Higgs boson and its interactions with other particles may not be accurate. This brings into question the predictions of the standard model of physics and may signify the existence of new physics that we have yet to discover. Further research and analysis are required to fully comprehend these recent findings and their implications for our understanding of the universe. The Higgs boson can be likened to waves created on the surface of a swimming pool when swimmers move across it. Similarly, when a particle interacts with the Higgs field, it causes a disturbance or ripple, like a wave. The Higgs boson is a quantum excitation of the Higgs field. When the Higgs boson was discovered at the Large Hadron Collider, it confirmed the existence of particles interacting with the Higgs field, just as seeing waves in the pool would confirm the presence of swimmers. However, the Higgs boson is incredibly short-lived. It exists for less than a trillionth of a billionth of a second, precisely 1.6 x 10⁻⁻22 seconds. This fleeting nature makes studying the particle extremely challenging, as it is created and destroyed almost instantaneously. To study the properties of such short-lived particles, physicists rely on their decay modes. The Higgs boson can decay in various ways or modes, depending on the specific conditions. The unusual event related to the Higgs boson involves its decay into another set of particles. Returning to the swimming pool analogy, imagine that the wave or Higgs boson in the pool becomes too large to sustain itself. In such cases, it needs to settle down. It does so by breaking up into smaller ripples or waves. These smaller waves represent other particles. Based on the initial size and energy of the Higgs boson, it can break into a pair of smaller identical waves, such as W bosons, Z bosons, or tau leptons. It can also create a mixture of waves and tiny bubbles, like a pair of leptons and photons. Here's where things become complicated. The decay process of the Higgs boson into two photons is not straightforward. It involves a convoluted mechanism known as a loop, where virtual particles temporarily appear and disappear. These virtual particles can include hypothetical particles that have yet to be observed, making their direct detection challenging. The decay of the Higgs boson into a photon and a Z boson is not limited to just the decay into two photons. This particular decay process has garnered interest in a new study. The Z boson is a heavyweight elementary particle, and along with the W boson, acts as a carrier of the weak nuclear force. Researchers at the Large Hadron Collider aim to investigate this rare decay process. According to the predictions of the standard model of particle physics, only a small fraction, approximately 0.15%, of Higgs bosons should decay into a Z boson and a photon. However, the experimental data collected from proton-proton collisions at the 8LES and CNS detectors between 2015 and 2018 tells a different story. Surprisingly, the data reveals that this decay process occurs in about 6.6% of cases, deviating significantly from the expected value. Both experiments identified the Z boson by observing its subsequent decay into pairs of electrons or muons. The frequency of these Z boson decays was found to be approximately 6.6%. 8LES and CNS, the two primary experiments at the Large Hadron Collider, employed strategic approaches to maximize the sensitivity in detecting the decay of the Higgs boson into a Z boson and a photon. They focused on the most common modes of Higgs boson production and utilized advanced machine learning techniques to effectively distinguish between signal and background events. As a result, they obtained the first evidence of this decay process. The observed statistical significance for the decay of the Higgs boson into a photon and a Z boson is 3.4 standard deviations, slightly below the required threshold of 5 standard deviations. However, the measured signal rate deviates from the predictions of the standard model by 1.9 standard deviations, indicating a notable result worth considering. This finding challenges the completeness of the standard model and suggests a potential need for extensions or modifications. Nonetheless, it serves as a robust test of the standard model and its predictions. Further advancements in precision and exploration of rarer Higgs boson decays are expected in the ongoing third run of the Large Hadron Collider (LHC) and future high luminosity (LHC). This study holds promise for deeper insights into the fundamental nature of particles and their interactions. Additionally, astronomers recently made a groundbreaking discovery of the gravitational wave background, which has the potential to rewrite physics.